part where you're actually doing this contraction, and there's the part where you're repeating it over and over again. And you have to repeat it over and over again because your probability of success was so small. If the probability of success was much bigger, you wouldn't have this problem. So one of the challenges is often in a randomized procedure is, can we avoid doing too much work with amplification because the initial probability of success is way better. And if we can do that, and if you get a probability of failure that's quite small, then we don't have to repeat it too many times to get a really small probability. So the question is, can we optimize this somehow, right? Without really, by coming up with a better process. And so, again, because it was just so clever, it was felt like, you know, I just want to show you how you can make a very tiny modifications algorithm. Now, this is not a generic strategy that will always work, so I'm not going to claim that it will always work for you. But it's something where, in this particular case, just a simple tweak to the way the algorithm works suddenly makes it a lot better. So let me maybe give you, let me give you the tweak, and then let me try to justify why the tweak should work, and then let me prove to you that the tweak actually does work. So the tweak is the following. And what it says essentially is kind of amplify in line rather than running the whole algorithm down to the end and then amplifying it then. So the previous process was run the algorithm all the way till you have only 2 vertices left. That gives you some probability of success, and then do this whole process over again. The insight here is to sort of observe that if you look at this way these probabilities cascade, in the beginning, you're making very good progress. All your choices are great because the probability of success is the probability of success is very high, right? And as you get towards the end, the probability of success starts dropping. Because in the beginning, you have lots of vertices. Your min cut is small, so anything you pick is going to be decent. But as you start contracting and contracting and contracting, you start getting more and more of a chance of picking edges from the min cut, and that's going to be a problem. So at the beginning, things are good. At the end, things are bad. Can we leverage that observation somehow? And so the observation looks something like this. So the new algorithm, so version 2 of the algorithm looks something like this. So step 1, well, not step 1. So the process is repeat twice. Okay. Run the contraction process for, get this right, until graph has size n over square root 2 plus 1. And when you look at this, just think n over a constant. Don't worry about y squared to y plus 1. Just think some n over a constant. So you're not running too much into it. You're just running it down to something like n over square root 2. Okay. And then step 2 recurs. So this is the entire process on the result. So what's going to happen is it's going to say, okay, I want to take this graph. I'm going to do this following thing 2 times, where I contract it down to n over square root 2, and then call the same process again, which means that also does 2 times contract down to the new n over square root 2, and then so on, so on, so on. Okay. And of course, remember that it's dropping by a constant fraction, square root 2 at every step. Right? So it's not like this process is going to blow up too much. It's going to be fairly small. So now the question is, sorry, another question. So now the question is going to be, first of all, what is the running time of the process? Okay. Because we know that it takes we can analyze exactly how long it's going to take. So we will do 2 things. We'll analyze this running time, and we'll analyze the probability of success. And they're both, not surprisingly, because of recursive algorithm, going to be involving recurrence. the running time of this process first, before you look at whether it gives you correct answer. So the running time looks something like this. So maybe someone can start telling me how to do that. T of n is equal to what? So look at the algorithm and tell me what you think is going to happen. So if you read from top to bottom, it kind of tells you what you need to do. So think this is like a homework problem, right? I give you an algorithm, write on the records that describes this one. Anyone?
T of n equals T of n divided by root 2 plus n divided by root 2 plus square of n.
Tell me.
It's like T of n divided by root 2 plus n divided by root 2 whole square.
Wait, where the plus is where?
Plus is after the bracket.
Plus?
N divided by root 2 whole square.
Would you like to explain this to me?
Because n divided, sorry, not n divided by root 2, just n square.
Okay, explain this to me.
Because each step is taking, I'm not sure.
You would like to comment on this proposal? Were you going to say something? Do you think you're saying something? You looked at me and you were about to say something.
Any step the graph is n by root 2 times of itself, and then every step actually is n squared.
So you're agreeing with this? Is that what you're saying?
No.
You don't know. Okay. Anyone else?
First it's repeat twice. So
Sorry?
it's saying repeat only twice.
So
we can't write this exactly. We have to like
how would you write it?
you write Tn equal to n square for the first time. Not h n because we are running with n by 1.
Well, okay, so I mean it's O of n, it's theta n squared, right? Because it's going from n to n over root 2. So it's running something like n minus n over root 2 steps of the process.
Yeah.
So it's going to be n times that, which is basically n squared. That part I'm okay with. That's more within a constant factor than n squared. But the two thing I think is important. The repeat twice. How does that get encoded? And it's the first line of the algorithm. So
Yeah. So as a style, next time we will run on
I think you're overcomplicating.
n square by 2.
And I think you're trying to be clever again.
Multiply outside by 2.
Is that what you're proposing?
I don't know, just shooting it up.
Like this?
Yeah.
Okay, what do people want this proposal? Does this capture what they're doing?
The resultant graph is n by, will you have it with your size n by?
The resulting graph after the step 1. Correct.
Yeah. So how is it n squared?
Okay, so one reason why that n squared is actually correct is because you're saying I'm running this process something like n minus n over square root 2 steps. Each step takes linear time because you have to look for the you have to sort of contract potentially a bunch of edges around two things. There could be lots of edges. So in the worst case, so take n minus n over square root 2 steps, each taking linear time. So it takes no more than n squared minus n squared times 1 minus 1 over square root of 2, which is theta of n squared. Right? So this will be basically n squared times 1 minus 1 over square root of 2, which is basically theta of n squared. Right? So maybe I should put theta. So that'll be more. What about the factor 2? Do we all like that? Do we have no thoughts on that? So again, think of what the algorithm is doing. It's saying, do something twice. What's the something it's doing? Well, it's running a contraction procedure, which you just said takes theta n squared time. And it's recursing on something of size n over square root 2. So it's doing this thing and this thing, and it's doing them twice. That's it.
The second run, the graph size would already be of
No. Repeat twice means repeat independently twice. Sorry. That means start the graph, do this whole thing, start the original graph, do this whole thing. You repeat starting at the beginning, right? So this process is done on 2 copies of the original graph.
And all this recurs on resulting graphs.
Okay,
Recurs the
good.
first-
So let me be more specific. So let me write this out differently. I'll put a little note here. Make 2 copies of G. Okay. Run the contraction process till the graph size till the graph Gi has size n over square 2 plus 1. Call it Gi prime. Recurs on resulting graph Gi prime. Does that help?
So when we get the min.
Sorry?
So we stop the recursion when we get the min cut. Or
We stop the recursion when we get under 2 vertices. Yeah, sorry. So again, zeroth step, because we should always have a base case. If n equal to 2, return cut. So I claim this is the running. This in fact is the recurrence that describes running time, because now you see I'm running 2 copies of the procedure, so that's 2 times whatever. In each copy, I do n squared worth of work because of that, and then I recurse. Okay. And in the end, you just take the best answer you get. So in other words, when you repeat this twice with 2 copies of the graph, you take the best answer you get from both. Right? So at the end, I will say, maybe I should have. Return smallest answer from each GI. Right.
But repeat twice really matters. I mean, when calculating the time complexity, because for example, if you take an algorithm which takes n squared, and you repeat the same thing again, which takes n squared.
Yes, but remember, I'm repeating a recursive process. So now what you're saying is that if I replace this 2 here by 10, does it make a difference? And to answer that question, you should ask yourself, if I have t of n is equal to 2t n over square root 2 versus t of n is equal to 10t n over square root 2, do you think they'll get different answers? Strictly different asymptotic answers for these 2 cases. Think of the master theorem. What are you going to get? You're going to get very different answers. So that 2 is important. I mean, it's a material. Because if you choose 2 or 3 or 4, it's going to change your answer. Obviously, you want to choose as little as possible. Right? I mean, if you think about the original algorithm, that corresponds to choosing a different number of it. What does it correspond to? It corresponds to replacing 2 by something else. It corresponds to replacing 2 by 1. For 1 copy of the graph, recurs down to n over 2, and then recurs, which does the same thing again. And recurs does the same thing again. So it's like taking the iterative process, breaking it up into phases, and just running it. So the original algorithm corresponds to a 1 here. We're now putting a 2 in here. So let's see what happens. Okay. All right. So what does the analysis look like? If you were to solve this recurrence, what are you going to get? So let's write this out more cleanly. Let's put 2t n over square root 2 plus, notice I can absorb the 2 inside. Doesn't really matter. Okay. This is a standard example of the master theorem. Anyone like to take? The way you should think about this is that you should write down 2 things. The first thing you should be writing down is n to the log of 2 base square root of 2, and then you should be writing down n squared, right? Well, what does this give you? This gives you n squared and n squared, right? So the overall running time will be
n squared. And log n.
n squared log n.
Yeah, n squared.
So this will give you essentially n squared log n. So the previous process had a 1, and you got n squared. This process has a 2, and you got n squared log n. So far so good. We haven't improved change the running time by too much. We haven't increased it by too much. But we better hope the probability of failure has gone down a lot. Otherwise, the whole point of doing this is wasted. That's the reason why we did this, right? We want the probability of failure to go down by doing a little bit more work. So now how do we analyze the probability of failure? As it turns out, that will be another reference. So let's look at, so let's say the probability of success. So let Pn denote the probability of success. Okay? When will this process succeed? Well, this process will succeed if at least one of the two steps, the two branches, succeed. Right? So we can write that P of n is equal to 1 minus something squared, where that something is going to the probability that the internal process fails. Right? Yes? Okay. What is the probability that the internal process will fail? The process of just running the contraction down and recursive. Well, the probability of the internal process failing is a probability of, wait, did I get this right? Hold on a second. Let me back up a second. Okay, so this, okay, so let's just write this one here. So P of n is 1 minus the probability of failure. Okay. Probability of failure is both sides, both repetitions fail, right? Now, both repetitions fail means this can be written as 1 minus repetition, okay, now I got it right. Repetition succeeds squared, right? Yes? Or rather, 1 minus the probability that the repetition succeeds squared. So all I have to do now is figure out what the probability is that one of the repetitions succeeds. Which means that I have to, if I go back to my procedure, I have to look at two things. What is the probability that step 1 succeeds? And what is the probability that step 2 succeeds? Both of them have to work. We know the probability that step 2 succeeds. That's recursion. That's just P of n over square root of 2. What's the probability of the first one that succeeds? And that's where things get interesting. That's where the crux of this idea comes from. We know that there's this telescoping effect, right? So the telescoping effect is basically, initially the probability of success is 1 minus 2 over n, then it's 1 minus 2 over n minus 1, then it's 1 minus 2 over n minus 2, and so on. Right? So if we're looking at the probability that the step 1 succeeds, so the probability that step 1 succeeds is equal to 1 minus 2 over n times 1 minus 2 over n minus 1 all the way up to 1 minus 2 over n over square root of 2 plus 1. Right? And we knew this telescoping trick, right? But since it doesn't go all the way to the end, we should rewrite this as something like, so look like what? N minus 2 over n times n minus 3 over n minus 1. The denominator here is going to be what? N over square root 2 plus 1, n over square root 2 minus 1. Right? What are the difference of 2 between these things? Okay. If you simplify everything in the intermediate step cancels out. What you end up with is something like this. n over square root of 2 times n over square root of 2 minus 1 divided by n times n minus 1. Okay? And if you simplify this, you basically get you have to adjust the plus ones and minus ones a little bit to make sure it's half. All you want to do is make sure it's greater than or equal to half. And again, you can see that because basically this is like n squared over 2 and this is like n squared. In the limit as n gets large, these other lower order terms go away. And this is the key insight, that in the beginning, like I said, in the beginning you're making very good progress. You're picking all these edges that are not part of the network because you've got so many edges, life is good. And what this is saying is that, look, if you go all the way from n down to n minus n over square root of 2, go from n to n over square root of 2, you're actually still got a lot of probability of success. It's half. Whereas when you go all the way to the end, it becomes 1 over n squared. So they don't go all the way to the end. Just stop here. And so this probability is half. And we already said the probability of step 2 being correct is p of n over square root of 2. So if we wrap this all up, the probability that the repetition succeeds is greater than or equal to half times p of n over square root of 2. Because you first have a half for the first part, and you need the second part to succeed. So both parts have to succeed for that repetition to succeed, so you multiply these two independent events together. Which means that overall the probability of success is greater than or equal to 1 minus half p of n over square root of 2 whole squared. Okay? This is not the easiest recurrence in the world to solve. It's not in the form of the Marshall theorem will help you, because you have the square term involving p of n over square root of 2. But you can do the analysis for this. Again, it's not something I would expect you to do just as a homework assignment, but I can tell you that and one way to check the answer to solve these records is to guess an answer and check it. It turns out you can show that p of n is greater than or equal to 1 over. And you can plug it into that. A very crude way to think about why this is going to be sort of 1 over log n and not like previously 1 over n squared is basically because of that square term. And it's very hard to explain why that works that way. That's sort of what happens. Yeah. Okay. So again, this you have to take my word for it, but you can plug it in and sort of verify. So this was the result. And so the upshot of all of this is that with this new procedure, it takes a teeny bit longer per iteration, n squared, overall, it takes n squared log n time. But because this probability of success is now 1 over log n, now based on what we saw before, how many iterations are you going to, how many times do you need to amplify to get a very high probability of success? You need to do the reciprocal of this probability times an extra log n, just to get a high probability log. So if you run this procedure log squared n times, so now we're saying, so run the new procedure, which itself is recursive. It has 2 little steps in itself. Right? Log squared n times, which means that the probability of failure, just like before we argued, will be 1 over n. Again, you can figure this out why, using the exact same reasoning we did before, why log squared n you should think of as 1 over log n times log n. So 1 over the probability of success times log n is what's going to do this. And the overall running time is going to be n squared log n times log squared n, which is equal to n squared log cubed n, which, needless to say, is way better than n. It's almost close to the time from 1 iteration, n squared. And so the point of going through this exercise with this somewhat boutique algorithm, which is very specialized, is to show you that sometimes with a randomized algorithm, the trick is not necessarily to make the algorithm faster, but to design the process so that the probability of failure is much smaller. Because then amplification will help you with that. All right, so let me put this back up here. This more complicated process. And remember, this module is what we're going to repeat log squared at times to give the best answer. So let me stop and take some sort of questions or thoughts or confusion as to what I'm saying. Yeah.
This thing of repeating twice.
Yeah.
Why are we exactly wanting to repeat it twice? Was it?
So here's why. We know that if you run down to n over square root 2 vertices, that process has a probability half of retaining an answer that's pretty good. Okay? So if you have a process that has a probability half of being pretty good, and you run it twice, you expect that it will be pretty good. So the idea is you do this twice because you want to do something that allows you to give a solid answer, which you can then do the recursion of. So it takes away that uncertainty in the first one. That's the intuition. That's not exactly how the analysis looks. The analysis looks at the records, but that's kind of the intuition for why we need to do it twice. And why doing it 3 or 4 or 5 times would be overkill. It would be even better probability-wise, but your running time will start going up like crazy. Because if you notice this recurrence, that 2 is very special because it's n to the log of 2 base square root of 2. If I put a 3 there, or a 4, or 5 iterations, that running time is going to go way up. So there's a trade-off here. So normally we think of trade-offs in terms of space and time. Here the trade-off is in terms of time and probability of correctness. By increasing the number of repetitions, you will make your probability of error get really small. But the penalty is that your running time will go way up. So what you're trying to do is find the sweet spot between very bad probability of success and a reasonably quick running time versus a very good probability of success, but the running time just gets terrible. And this 2 turned out to be a sweet spot. 1 was not good enough. 3 would be terrible. 2 is just right. And this is something that will happen more often than not in a randomized strategy, where you're trying to balance probability of error versus time. More time will get you a better result. So if you think of amplification, that's a classic example of this. You're running it more time to get a better probability of error. And amplification represents one kind of trade-off, but it's not the best kind of trade-off as we're seeing. The amplification gave us n to the 4th to get the probability we wanted. Here, we can do a much better trade. And so that's the advanced sort of world of randomized algorithms involves that kind of thinking. How do you trade off time and randomness and probability of error to get what you want? And again, this is not something we will go to in great detail here in this class. That's for more advanced class. But I just want to give you sort of a window into that world of what it is. Other questions? Yeah.
Why n over root 2? One thing is I think because you want half probability. But why half? Why not?
So clearly the root 2 and this are playing off against each other.
Yes.
Right?
Because
So they're not free parameters.
Yeah,
There's a root 2 because there's a 2. Right. So so one argument you could make is would it work with say root 3 and 3 or or 2 and 4? It won't, because if you look at how so the other way to think of the half is that you're doing this telescoping multiplication. You're doing n minus 2 over n times n minus 3 over n minus 1, and you're getting that balance point. What you're saying is you could keep running it for longer. What are you going to get as a probability? Remember, the probability starts at very high of success. It's n minus 2 over n. At the end, it's like 1 over 3, which is quite small, right? So somewhere it goes from 1 to 1 over 3, and very quickly it gets to half. So the probability sort of landscape of what's happening as you contract more and more, it's like, okay, this is 1, this is 1/3, it's kind of coming down like this. You don't want to be in this range where the probability of success is low. You want to be in the range where the probability of success is high. So you want to keep going down as far as you can while it's still worthwhile, then you want to cut off there. So that's sort of where I don't know if root 2 is sacred, but you need something like that to get constants there. And it would be a helpful, if you were curious, you could try playing with this number. Okay, so when I run down to n over, the way I would do it is, okay, run it down to n over L for some unknown parameter L, work through the entire analysis. This will give you some running time as a function of L. There will be some trade-off in terms of probability of error. Solve for the best value of L. And I would not be surprised if that's exactly how they would do. A lot of times in algorithm design, you don't know ahead of time what the right parameter to choose. You just let it be unknown. You solve the whole thing, balance out the probability of error in the runtime. It's okay, what best value do I need?
And equal to 2 and running how many times you run and how much you reduce, they are connected.
They're connected. They're not independent of each other. That twice and that square root 2 are connected. Yeah. And that's why sometimes when you look at an algorithm after the fact, you're like, well, why twice? Why square root 2? It's only when you look at the analysis, you realize, okay, these are not independent parameters. They're related, and they just happen to choose the best trade-off for those parameters. Yeah. But if I wrote them just in terms of arbitrary parameters, it would look terrible. It'd be very hard to see what was going on. So sometimes you have to kind of look at the algorithm and look back at the analysis and say, okay, this is in the proof of the correctness is where all these choices are going. And that's sort of, there's a larger lesson here about how to read theoretical papers. This is one of those lessons. Sometimes when you see a theorem and you see a proof, the numbers don't matter so much as the relationships. And that's why I was like, just a constant. Because what I'm saying is that value of the constant is something that's optimized. What's interesting is the fact that you have this relationship. This takes experience. It's not something you will be able to do immediately. But over time, as you read theory papers, you will start learning to look for these things. Right? And so I'm just telling you right now, that's how you should look at it. All right. Well, any more questions? Okay. What I want to move on to is another example of a randomized algorithm, but something that is so ubiquitous everywhere that it would be a sort of almost a criminal shame not to talk about it. But it also helps us introduce another way of thinking about analyzing the behavior. So the problem that we're looking at is sampling. Probably the most common example of randomization you will ever see. If you never take a computer science class in your life, you will come across sampling, which is basically, I want to estimate something. I don't want to look at everything. I sample a few things. I build my estimate from that, and I hope that it's a good estimate of what I'm looking for. Okay? So, elections are coming next year, so I'm told. Polls will start coming out. And they will start blathering about how this poll means this and this poll means that. But how do they do a poll in the first place? They don't actually ask everyone what they think. They sample. You sample some number of people, you ask them what they think. You ask them who are you going to vote for, and they give you their answers. You tally up the answers from those people, and you say, oh, according to this poll, there is a 53% chance that this candidate will win, or a 37% chance that that candidate will win, and so on. This is all totally arbitrary. Where they get this? So why should we? And by the way, and this happens every 4 years because of mathematical inaccuracy of the population in general. Everyone will say, well, you can't. That's just a poll. You can't predict what's going to happen from a poll. The polls are always wrong. Blah blah blah. Well, this is about true and false, right? It's false in that, in fact, polls can give you a very good estimate of what's happening in a population, as long as you sample right. It's often the second part that gets forgotten. So that as long as you sample the right part is also related to how do you analyze the result of the sample. Right? How noisy is it? This is a randomized algorithm. You are introducing randomness and deciding who to ask for an opinion. And you're good. So today we're going to look at one example of this, polling example of this if you wish. And we're going to show you how this analysis works, how it's a randomized algorithm, and what kind of basic tools and statistics we need to analyze it. We're going to introduce some very, very important concepts in randomized algorithms, an idea of looking at the scale of a distribution and how to analyze the behavior of a team. Okay. All right. So let's set up the problem. So we have a population of people. So let's say there are n people in the population. Right? And let's say this is, this is the population of people who are actually voting. Right? So they all vote. They vote for one candidate or another. And again, to keep it simple, we'll just encode candidates by numbers. So there's one candidate labeled 0, one candidate labeled 1, and people are voting for it. So of these n people, some n0 people vote for 0, and some n1 people vote for 1. Okay, and n0 plus n1 is good. You want to know, you want to run a poll to see, hey, at this moment in time, who's likely to win? And of course, we know that whichever of these two numbers is bigger, that candidate will win. But we don't know what that number is, and we can't go and ask them. So our procedure, our sampling procedure, is going to be: we will sample uniformly. That means every person gets a chance of being picked. Small n people. So it's a sample. And we'll ask them what they think, who they're going to vote for, and they're going to tell us. So there'll be, n0 and n1, as usual. So n0 of the people we sample will vote 0, and n1 will vote down. And we want to, now obviously here we can say, okay, which one is bigger? And what we want to know is, can we reliably say anything about the actual outcome based on the outcome from this process here? Okay. This is the core of every sampling procedure. Can you say something about the population? So in statistics, I'll call this the population, and let's call this the sample. Can you say something about the population from the sample? And that's the question we want to ask ourselves. And so we want to say this a bit more precisely. So in particular, what we want to say is, so let's sort of set up some basic sort of criteria, right? There are different ways we can talk about, is this reliable or not? So, so let's first ask the question, and let's just talk about the people voting 1 for a second. What can we say about the relationship between n1, small n1, and capital N1? Notice that n0 and n1 are random variables, right? The number of people who vote for a 1, it's a random variable because it's some function from the event space to a number. Number is the number of people who vote. It's a random variable, so we can talk about its expected value. What do we expect its value to be? So let's ask ourselves the first question. Okay. What is the expected? So how do we do this? So we could ask, how do we estimate n1? Well, sorry. So the way to do this is to write n1 as a expression of a series of other random variables. So in particular, we can say that the random variable n1 is equal to the sum of xi, where xi is 1 if the ith person votes 1 and equal to 0 otherwise. Right? And so the expected value of this random variable is the expected value of those things. Why this is helpful is because of a particular property that we rely on for expected values. So the expected value of n1 is equal to the expected value of the summation of xi. And there's this thing called the linearity of expectation, which means that if you have some kind of thing that you want to compute the expected value of, then if that thing can be written as a linear function, then the expectation of the linear function is a linear function of the expectation, which means that here I can swap the sum and the expected value and say this is basically this. This is probably one of the most important properties of the expected value. You can prove this, and it should be hard to prove because linearity itself is a linear function. You're just adding a whole bunch of things in the linear properties. But now we can ask ourselves, well, what is the expected value of a single variable, which is either 1 if they vote for 1 or 0 otherwise in our sample, right? And these are all chosen independently. So we're going to assume that we poll people with replacement, which means that when we sample a person from the pool and ask them their opinion, it's possible we sample them again later. So we sample a person from the pool, ask their opinion, write it down. And we sample a person from the pool, ask their opinion, write it down. We ignore the fact that we may have asked them the question before. This will make our analysis a lot simpler. Okay. And it turns out to not really affect the overall analysis. So if we have this summation here, where this is basically 1i for every person in the pool, right? So this is 1 if the person votes for 1 and it's 0 otherwise. What is the probability? So we can write this as the expected value of xi, since it's a binary value variable, is equal to p1 times 1 plus p0 times 0, which is where p1 equals to the probability that xi is equal to 1, and p0 is the probability that xi is equal to 0. Well, if this is 0, we don't care, so we just need to know what p1 is. And what is p1? What is the probability that a randomly chosen person from the pool is going to report a 1 as their answer? Well, we know the answer to that because there are n1 people who will vote 1. A randomly chosen person will be in the pool of people who will vote 1 with probability n1 divided by n, capital N1 divided by n. Right? So p1 is equal to capital N1 divided by n. Okay? And this number is special, we'll just call it P, right? The probability of a 1 vote, right? And therefore, the expected value in our sample is the sum of P for all entries, for all sample items that we pick. So it's n. And this kind of makes sense, right? What we're saying is, look, we know that in the general population, 53% of the people will vote for one candidate. If we take a sample of size 10, what we're saying is that we expect 5.3 people to vote, but the expected value is going to be 5.3. That's what you expect us to do. That's a good news, right? It's what's called an unbiased estimator, right? That the fraction in the sample should look like the fraction in the actual population, right? Because we're saying the expected number of people who vote for the candidate is n times p. Then the expected fraction of people who vote for the candidate in our sample is n pi p divided by n, which is p. So in fact, our sample correctly captures, on average, right, the behavior of the overall population. Yes? So can you see why this is a good thing? That you want your sample to look like the population? Okay. But that's just the average. There's noise. Every time I pick a sample, we're going to get a different answer. All we're saying with this is that if we ran this process 100 billion times, wrote down the answer each time and took their averages, that average would be the exact value. But we're not running it 100 billion times, we're running it once. So this answer is going to deviate from the actual value. It's not going to look like NP every single time. Like if you toss a coin that's fair coin, it's not going to be half heads, half tails. It's going to be heads sometimes, tails sometimes. It's going to be something or the other. So in order to know whether our estimate is good, we have to understand how far it deviates from its expected value. In other words, we want to know, and this is the key to everything, what is the probability that n1 minus the expected value of n1, right, is larger than 0. So I'm going to sort of highlight this, because this is a central object of study in randomized algorithms and probability. This is what is called a tail bond. Okay? And pictorially, the reason why it's called a tail bond is because of this. So let's draw the probability distribution of this random variable. It's a random variable, so it's a probability distribution. It can take on many different values from 0 up to whatever. So let's say its distribution looks something like this. a convenient distribution. It's got a a mean that looks sort of reasonably clear. So let's say the mean is somewhere here, right? Okay. And now we're saying the event we're looking for is that the actual value is reasonably far from the mean. So if you think of t as a distance, let's take a distance of t on both sides. Okay. What we're asking is, what is the probability this happens? In other words, what is the area under the curve here? In other words, what is the tail of this distribution? The reason we want the answer to this question very quickly is because we would like to believe that every time we do a sample, we get this answer. We know we're not going to get the answer because we've got a distribution. So what we'd like to know is, well, how often are we significantly far away? So obviously, if you make this number big, the probability goes down. If you make this number small, the probability goes up, right? So there's a kind of a trade-off here between what we choose to be our distance from the value we expect and the probability we want to see. And so analyzing this behavior is what is called looking at the tails of this distribution, which is going to be a very, very important thing to study for all randomized procedures, because we're saying, look, we know this expected behavior is good. How often is it not going to show us expected behavior? So for example, a distribution, again, I'll be very quick. A distribution that looks like this has very, very small tails. You're happy with the behavior looks like this, very consistent. A deterministic algorithm looks like this. There's just one spike. It always does the same thing every single time. An algorithm we would not like is one that looks like this. So now, again, you look at this distance, you get a lot of stuff where you can go wrong. So we want to know the difference. We want to know whether we're in this regime or this regime for our algorithm we're analyzing. And to do that, we need to understand those tails. And so you will find that a lot of study of randomized algorithms involves 5-line algorithm and pages of analysis of this. Because that's the key thing to study. And next time, that's what we do. Okay? Hey, what's up? I didn't say it's optimized. My suspicion is that, but it does work. Try it. Try it. Yeah, thanks a lot. You know the upload. Yeah, just make sure to tell Chris that it's for nothing. Because you want to do so much of it. Just remind us about these
like this amazing speech, just out of like thin air. And I'm like, probably not. But if Shakespeare's writing, and you can make some great speeches, because you know what's happening there. So hard. Well, Shakespeare's dead. Try. You might get points for trying. No. We're waiting on speeches that would be appropriate. We're going to be talking about this.
So you guys can stand for the speech.
No. You at least know it. Yes.